All right. So, well, welcome back. I hope you all had a nice break and were able to relax a little. Just a heads up, I have not yet assigned your projects. I want to do that today, and by the moment that I send the instructions to you is when you're going to have 2 weeks after that to conclude it. So, I'll try to get to that today. Um, just so you know. Okay, so we finished with our last time was our repeat and measure exercise on the experimental data. So up until now, we've only seen analysis of variance, where in our case here, our response variable, so the y on our formula, was always numerical, and our explanatory variable, so the x on our formula, were all categorical or factors. Now we're going to shift a little bit and get into a design where our response variable is still going to be numerical, but now our explanatory variable, so the x on the right-hand side of our formula, is also going to be numerical. So that is a difference. And if you think about it, if your explanatory variables are factors, then you're running analysis of variance because you're interested in the mean of the levels of those factors, right? So we saw before, in our cases, we were treating nitrogen rate and potassium rate as categorical because we wanted the mean of those treatments or the mean yield from those treatments. Now, if they are numerical instead, there's going to be a difference. You cannot get a mean of a variable that's numerical. Instead, we're going to have to run regression on it. There are different types of regression. I do expect that you already have had exposure and experience with regression. This is not going to be an intro to regression class. Instead, this is going to be a class or an exercise where we're going to be trying different types of regression that include both linear and nonlinear, with a very specific goal in mind. And I'll get more into that once we start the exercise. But so today we're going to be starting with regression, very applied regression, and we're going to be exploring both linear and nonlinear regression models. All right, so for us to get started with today's exercise, you will have to start your setup for a new project. If you recall, you do start that on GitHub first. So I want you to go to your own GitHub repo and create a new repository called 07_reg for regression. That's going to be the first step. So please go ahead and do that. And again, the steps of what you're doing are part of a lecture that we had previously. So that was the lecture on January 23rd. It has all the steps for you to do this. So the name again is 07_reg is the name of the repo I want you to create. These are the slides with those steps in case you want to see, but there are 3 slides here and I'm only showing you one. So if you want to go to each one of them on your side, these are the slides from the class on January 23rd in our roster, our schedule. So again, what I want you to create is 07_reg for regression on GitHub first. So you don't need a description, make it public, add a README file, and add a gitignore for R. Once you do that, you're gonna click on that HTTPS URL and copy that. And then coming back to your own computer, you're gonna launch RStudio, do a new project, version control, Git. You paste the URL that you just created above in the repository URL field. you can leave blank the project directory name. And then on the create project as subdirectory of, you want to browse to the main folder of the course. So you can just go to the folder where you see all of the previous projects as well on your computer. So we've been, well, I guess this is the seventh time perhaps that we've, or maybe not seventh, but fifth time we've done this. So I hope that you are getting somewhat familiar with it. And again, if you need more, if you need to look at the previous steps, you can check the presentation from January 23rd on our class website. After you do that, as you know, the next step is going to be for you to launch the 2024_DSA on your computer and do a Git pull on your RStudio. That would bring you, there is one new partial script that you can copy that script from 2024 DSA and into, well, I guess I have not asked you to do it, but when you do finish this step that's on the screen, you're gonna have, it's gonna launch your RStudio for you, and you can go ahead and here you can create the code, data, and output subfolders as we've been doing by default. If you want to do that through RStudio, you can click on that plus folder icon right there, but you can also do this through your computer file system. And then once you do that, from the 2024 DSA, you're gonna have 3 new files that I want you to copy and paste into 07 reg. One of them is going to be under 04 class code. That is the 0312 regression partial. So I want you to copy that into the code folder of 07 reg. And then lastly, on the 03 data, I want you to copy the ior.png and the reg.csv into your data folder of the 07_reg projects. All right, anyone needs help or clarification about the steps that we just talked about? I want to share here after you're all done, what you should be seeing is you have your 07_reg subfolder inside of your class main folder. Inside of that 07 reg, you should have, well, I have 2 scripts, you should only have 1. So you should have the partial script here under code, and under data, you should have the ior.png and the reg.csv inside there. Once you have that, you're ready to start the exercise. If anyone needs more time, let me know, and I can give you another moment. If I don't hear anything, I'm gonna start moving. All right, let's get moving then. So once you've done all the setup, we're ready for the exercise. Please go ahead and launch the 07 reg rproj. So you're operating out of that project. I already have that here on my side. When you launch it, if you cannot see the code yet, you can, on the Files tab, click the R blue button that takes you to the home folder of this project. go on code and launch your partial code. Again, if you do want to have your outline open on the side to help you navigate this script, you can do that by toggling the outline on off button. This is going to be a somewhat long script, so that may come in handy for you. Okay, so today I'm bringing a new data set for you. We're not going to continue using the previous one, mostly because there was a weak response of yield to both nitrogen and potassium rate. So I'm bringing you here a new data set that is going to be slightly different in concept. So our goal here is going to be, we're going to explore this data set where we have corn grain yield measured at 5 different seeding rates. And this was run as a randomized complete block design. So that's going to be part of our models as well. We want to incorporate that properly. So here's if you imagine now, here's what's going to happen. We have yield as on the y-axis as a numerical variable. We have seeding rates on the x-axis treated as numerical as well. Because of that, we're going to be running regression models. Our goal here is to, once we start plotting this, you're going to see this relationship, but our goal is going to be to select a regression model that best describes that relationship. Once we select that model, we're going to use that model to determine what was the optimum seeding rate that, or what was the seeding rate that optimized yield. This is the goal here. We see this a lot in agriculture where we're increasing a certain level of an input on the x-axis, and we want to see the effect of that on yield on the y-axis. Today, we're going to be training or running 4 different models: an intercept only, a linear model. And when I say linear here, I do want to say that what I mean by that is a intercept plus slope linear model, a quadratic model, which has curvature, and then a linear plateau. Something I want to point out here is that the first 3 are considered linear models. And this can be a little bit confusing because we say a lot of times we refer to a intercept plus slope model as being a linear model. That's what I'm doing here as well. But in terms of the proper nomenclature of these models, when it comes to if they're linear or nonlinear, the first 3 are linear models. The last one is the only nonlinear model. When we refer to that, when we say that a model is linear or nonlinear, we're not talking about the shape of the curve when you plot that model. That is not what we're talking about. A model is linear or nonlinear in relation to its parameters. So a linear plateau model is going to be nonlinear because it has a nonlinear behavior of its parameters, as we're going to see here in a moment. But just wanted to make that distinction there. We're also going to use Bootstrap to create confidence intervals around regression lines. When we get to that, we're going to talk a little bit more about what is Bootstrap and how we're doing that. Finally, we're going to compare all the models using a k-keys information criteria. We've done this on the previous exercise already. If you recall, lowest values are better. And then once we determine what's the best model among the 4 candidates that we're running up here, we will then use regression to find the level of input, which in this case is per hectare, that optimize crop output, which in this case is yield. Okay, so just giving you a little bit more background here. You know, I would imagine that in your disciplines, most of you may be working with some type of inputs that you can change the amounts, right? So that, in my case, most of the time that is fertilizer, but this could be pesticide. It could be irrigation volume. It could be even temperature or air relative humidity if you have controlled environments. It could be things that may not even be as intuitive, like planting date. So if I have I plan, my treatments are planting maybe like every 2 weeks or every week, and I have planting date now as my input that I'm changing. So there could be many others here, and I just want you to think about this on your own disciplines and how can you relate these concepts and whatever that is that you can find for yourself. Today, we're going to be looking at sitting rate, but that sitting rate could be any other numerical input that on your area of expertise, you would be changing. And in our case, we are looking at yield, but this does not necessarily have to be the case. It could be any other numerical output that you analyze here. So it could be, for example, plant height, or maybe anything that you would try to optimize, which most of the time is in relation to plants. But if you're trying to optimize something at the soil level or any other way, that variable could also go on your y-axis or your y response variable. Okay, so again, the main difference here, and I do want to make one parenthesis. In our previous exercise where we had potassium rate and nitrogen rate, we treated them as factors because we wanted to know the mean yield for each one of the levels of potassium and nitrogen, right? We could have, if we had treated them as numerical instead, that would have been a regression instead of an analysis of variance approach. So again, with a regression, it will depend on what model you're running, but you could be interested most of the time in the intercept and the slope. And in our case here, again, I want to mention this, we're not using that data set to carry over because we only had 3 levels of nitrogen, 3 levels of potassium. And also there was not a very strong response to yield, if you remember the box plots we made to understand that. So that's why I'm changing data sets, and I'm going to show something that is more, perhaps easier to understand this concept. So anytime that you have this input versus output numerical relationship. So remember, both your input, in this case, sitting rate, and your output, in this case, corn yield, are numerical. We will have a regression approach, and a few different patterns can emerge. So this is a figure. I'm just running this on my side. You also have this figure, but this is a figure to just illustrate a little bit of that. So for all of these 4 plots here, we have yield, a numerical variable on the y-axis. We have sitting rate, our numerical variable on the x-axis. And we have 4 different patterns here of how those 2 things can relate. These are just 4 examples of how this could be related, but it doesn't even have to be this way. There are other models that could perhaps fit here. I think these are the most common, at least in my discipline. So I want you to take a moment to look into these 4 behaviors, because I will ask some questions here, and different people can help me out. So the intercept model, so the first model here, so if we just focus on this one for now, what is happening here? Can anyone interpret this plot for me?
No impact of the seeding rate on yield.
Okay, so intercept, no impact of seeding rate on yield, right? So this means that as we are increasing seeding rate, our yield is not changing. If those data points are the ones you observe in your model, on your data, then the intercept only model is going to be your best model, right? That's what's going to fit the best your model. And this happens a lot. I've seen this with seeding rates. I've seen this with fertilizer rates. This would be common in fertilizer rates, for example, if you're applying a nutrient that is not limiting. So let's say you go to this site here, you take soil samples, and then your potassium levels that are coming from the soil are all greater than the minimum threshold you need for a given crop. So applying more potassium here would probably not increase your yield, because that is not a limiting factor. We see this a lot. Okay, so can someone else help me if I want to look at this data and determine what is the optimum seeding rate, okay, what would be that case if you have if the intercept model is the best for your data? What would you recommend that is your optimum seeding rate in this case? What did you say, Relisa? 40, right? I agree with that, because if if you are increasing that input and there's no impact on yield, then, I mean, really, you could apply any rate here that would get the same, but why would you use more input if you don't have to, right? So 40 would be the optimum here. All right, let's move on to the linear case. So the linear, well, what is happening here? If someone else that hasn't helped me yet can help me interpret this next plot here. Yes, so Benita said, as we increase seeding rate, we're increasing yields. So this, so remember, we're working with biological systems, right? Biological systems all have limits. Does this model mean that if I keep increasing my seeding rate to infinity, I will increase my yield to infinity? Probably not, right? There is going to be a biological limit here. When I see this type of relationship, what comes to my mind is that the levels that I selected for my seeding rate were not high enough for me to achieve that biological limit, right? We see this sometimes with nitrogen. So with nitrogen, maybe you have a year that it was like you really needed to apply more nitrogen, but your treatment levels for nitrogen rates, the maximum level was not high enough to provide all that potential that the field had. And in that case, you do not see a plateau. You do not reach the biological limit because your levels here did not attain that. So let's say that perhaps if you had continue increasing, well, in this case, seeding rate, let's say that your optimum would be, so you would plateau out at around 160, right? Within the levels that you had in your study, you did not achieve that biological limit, and therefore this is what we see. Okay, so now if we think about this linear case here, what would be your optimum if this is what you have? If someone else that hasn't helped me yet can help me with it. Okay, so Anis said the maximum seeding rate. So in this case, I mean, I agree with that. In this case here, since we have not achieved that plateau level, we would recommend to apply the maximum here, as that is giving us the maximum yield. All right. Now let's take a look at this quadratic relationship now. Can someone else help me to understand what's going on here?
Well, yeah, around 80, considerably 80, and after that, goes down.
Nice. So Anis Sabedi told me that as we are increasing seeding rate, we're increasing yield until a point, which here is probably looks like it's between maybe 80 and 100, maybe around 90. And then after that, it starts decreasing. This is something we see a lot, especially with seeding rates. Why is that? Sometimes with seeding rates, what happens is this behavior here is very common because, as you know, if you think about it, you have two extremes. One of them is to have one plant per hectare, right? That plant's going to be highly productive by itself, but on an area basis, it's going to be very inefficient. The other end of it is going to be to have, I don't know, 1 million plants, or 1 million, probably that's, well, we can think about it. That's a quite large extreme. So 1 million plants, whereas normally we would have somewhere between, I don't know, depending on the crop here, let's say that number would vary. In this case here, if we're looking at, so this is 1,000 seeds per hectare, ranging from 40 to 120,000 seeds per hectare. So if we have 1 million, we have way too many plants. They're they're competing with each other so much that really no one's going to do well here. So our yield's going to be low. So there's an optimal level between 1 and 1 million that we're looking for, right? So we need to find that level where the competition between plants or among plants, there's going to be some competition, but that on an area basis, it still allows yield to be optimized. This is normally what we see, because after you pass that point, then your inner plant competition becomes so high that you start losing yield at that point, right? So that's exactly it. All right, so what about this next one here? So the linear plateau. What can someone else that has not helped me yet, help me to understand what's going on here? Jonathan, what do you think?
That from 40 until 80, there's a linear increase of you. And then that's on the at 80 becomes the constant.
Yeah, so what Jonathan was saying here is that from 40 to 80,000 seeds per hectare, we have this linear increase until a point, and then it plateaus out after that point. So this model here sometimes is not the most biological sensitive, I guess. But it could happen that within the levels of your treatments, you see this plateau, this continuous plateau after the optimum. It doesn't mean it would always keep like that. So again, if you keep increasing your levels on the x-axis, at some point, you would expect that this would start decreasing. But you could have this function be the best fit to your model in case in your levels, you did not see that decrease afterwards. All right, so, these are perhaps four of the most common relationships that we see in this case with an input on the x-axis, seeding rate in this case, explaining an output, in this case, yield. We see these different behaviors. Okay, so let's get started with our coding part of the exercise. I have one new package here for you. I believe that's the only new one that I left you the code here for you to install. So if you just want to uncomment that, the package is called NLRAA. You can install that and then comment it off so you don't have it active. And once you install it, you can go ahead and run this chunk to load all the packages we need. So our first step here is going to be to import our data. It is that CSV file that I shared with you that I hope you have moved into your data folder, right? So the rag.csv. Because it is a CSV file, we're going to use our read_CSV. So read_CSV. And then you can just browse to that file. So /data rag.csv. If you printed, so this was a randomized complete block design with 4 reps. So we have rep here 1 through 4, and it is being interpreted as double, so as numerical by R. We have our seeding rate in 1,000 seeds per hectare, where we have 5 levels ranging from 40 to 120. And then finally, we have our yield in megagrams per hectare or tons per hectare. And this is corn. So, and also we have 20 observations. I do want to do some light wrangling right here. So if you just come after your read CSV, let's add a pipe. I do want to use the function clean names just to get these standardized to lowercase. And also, so in the previous exercise, remember we were talking about that rep should be factor. Block should be a factor here because block 2 is not 2 times larger than block 1, right? That is just the way that we refer to them numerically, but they don't have numerical meaning here. So let's go ahead and use a mutate where I want to say rep equals to factor rep. So you want to have your blocks being factor. And again, notice here on the previous exercises, we had nitrogen rate and potassium rates that were also interpreted by R as numerical. And on the previous exercises where we wanted to run analysis of variance, we had transformed our potassium and nitrogen rate to factor as well. We are not going to be doing that here with hidden rates, because if we do that, then we run an analysis of variance. I want to run a regression here. I do want you to notice that if your treatments are different amounts of given input, like we have here, like we had previously, that same data set can be analyzed in two different ways. One of them would be as an ANOVA model, where your question you have is, what is the mean yield difference between 40 and 60 and 60 and 80, right? So we're interested in the mean response of these levels, then you run analysis of variance. If, however, you don't care for those means, you're interested in the overall behavior. You want to know, as I increase in rate, what happens with yield? Is it linearly increased? Is it a quadratic response? Is it a linear plateau response? If that is your answer, if that is your question, then you should treat sitting rate as, or this treatment here, whatever that would be, in our case, is sitting rate, you should treat that as numerical. Again, regression, numerical Y, numerical X. If it's ANOVA, numerical Y, categorical X, right? So if your design, again, has a treatment that could be treated both as numeric or categorical, depending on your question, you can play with this. However, if your treatment here was, for example, variety, there is no way you can treat variety as numerical, right? That is a name. In that case, you can only run analysis of variance. There is a distinction here. All right, so I'm just giving you some more information here. It was in our CBD, looking into the effect of sitting rate on yield, and then sitting rate had 5 levels, 40, 60, 80, 100, 120, and then corn yield was measured in megagrams per hectare or tons per hectare. All right, as always, I always encourage you to check your data doing EDA. So let's start that with the summary. So if we ask for a summary, I left you the code there. We can see here, I mean, really in this case, the most interesting is that yield column, where we see yield is ranging from about 7.87 to 15.65 megagrams per hectare. These values look good to me. They make sense. They're biologically possible. No reason to believe there is something wrong with this. All right, I do want to make plots as well, right? I think plots are very helpful for us to understand what's going on. So my goal in this chunk here is to create a box plot. So with that, let's begin with ggplot. The first thing is the data. So the data is called reg_dfw. We give it a comma. We call AES. So I want to print reg DFW below, so just we can see, I want to have my seeding rates on the x-axis. So x equals SR, 1,000 seeds per hectare. On the y, I want to have yield, megagrams per hectare. And then, well, if you just run this, as we know, it's going to give us that canvas. It's not going to have anything in it because we have not added any geomes yet. So we can come back to the code, add a plus, and I want to ask for a geome box plot, as we've been using this a lot to look at data distributions. What is going on here? Why do we get one big box plot? Yes, sitting rate is numerical. That's why it's giving us one box plot for all the sitting rates combined. I want to show you something. I mean, if you want to do on your side, you can do, but just remember to remove this. If I really wanted to see the box plot of each individual sitting rate, again, sitting rate should have been a factor. I can do that kind of on the fly here without changing the data, just by treating x equals sitting rate and have factor wrapped around it. In this case, we get a box plot for each of the levels. Remember, if your goal is to compare the means of these box plots, this would be analysis of variance, and sitting rate would have to be categorical. In our case, that is not our goal. The answer here is really that a box plot is not the best one to understand. It's not the best geom for us to visualize this relationship. So on the next plot here, on the next chunk, let's actually create a plot that is better suited for us to understand this relationship. So I left you the beginning of the code as we had just done above. What would be a geom? So not geom box plot. What would be a geom that we could use here that would help us understand this relationship? Points, right? Geom points. So let's go ahead, add a plus, geom underscore point. All right. That looks like, that this is we can see those points there of sitting rates impacting yield. Something else that when we do have two numerical variables, so numerical on the y, numerical on the x, and we want to better understand that relationship, we can, if you recall, we've used this before, we can use geom smooth to add a smooth line and give us an idea of this relationship. So if we add a plus, let's use geom underscore smooth. So just add a geom smooth. This is what it looks like. So it looks like we have this quadratic relationship, I guess, right? Or at least with so geom smooth is allowed to vary or to be a wiggly line here. So I'm not fitting a quadratic fit here. This is a loss regression where it's really just allowing this blue line to be wiggly. And it looks like quadratic in this case. So that would be, at this stage of EDA, maybe that would be my hypothesis, is that the relationship that we're going to find here is going to be quadratic. But we have to test that with actual models and compare them. All right, any questions here before we start the modeling exercise? All right, let's go for it. So now we're going to be fitting 4 different models and assess both numerically and visually which one fits this data best. And after that, we're going to select that model to estimate the optimum sitting or the sitting rate level that optimizes yield. So the first model that we're going to do is going to be the intercept only. I left you that options contrast, so make sure you run that to get the proper matrix parameterization. So this is a randomized complete block design. I do want to run blocks as random. So this is going to be a mix effect model. We have used a couple of packages and a function from each one of those couple packages to run mix effect models. Can anyone perhaps help me with, well, if we think about it, what was the package that we used to run mix effect models? LME4, right? Okay, so that is the package. Can someone else help me with the name of the function we were using from that package to run mix effect models? And LME, we use that for the nonlinear models. And we could use that here, but I'm thinking of a different one. The one that we started using, LMER, yes. So we use LMER, so let's go ahead and call that here, LMER. So our data, I just want to print that below so we get the variable names again, is reg underscore DFW. I'm just going to print that to look at the column names. So we're going to have yield in milligrams per hectare explained by, and we say that by giving the tilde. The random effect part of this model is block. So we're going to give the open and close parentheses, 1 vertical bar rep. Rep is the name of that column. And then we give it the fixed effect parts of the model. So here's something different that we have not seen yet. What I want to run here is a model that only has an intercept. In our syntax, if that is all I want, I don't have to specify any fixed effects here because that already is calculated for us. So if you remember on our ANOVA tables, there was always an intercept line, even though we were not asking for it. That's because every model has at least an overall intercept and then the factors that you specify after. So if I just want that intercept, I just leave it like this. I just have my random component and then the intercept is implied already. So after this, just to complete, we have to give it a comma and need to say data equals reg underscore df. So if we run that and we ask for a summary, this is going to be the regular LMER summary we've seen. It's going to have the random effects part of it, which is just giving the rep and the residual. Remember, the rep is the random effect related to the variance component from the rep effect. We have talked about this in different moments. And the residual is the error associated with the residuals of the model, right? So the variance of the residuals. And I'll notice that on our fixed effects table, we just have an intercept entry here. So that is saying that intercept was estimated at 12.17 because the response variable is yield, is just telling us that the overall mean of the yield in this data set is 12.17 megagrams per hectare. This is what this means. And that intercept was highly significant, as we can see here on the p-value. As with every model, we have to check model assumptions. I think I left you all the code there for this. Yeah, I left all the code, so you can just run that. We're using the augment function, entering the standardized residual. And in this case here, we had not done this before, but I'm left joining with the original data set. And the reason for that is because we did not have any, let me just run this for you to see. So running just the augment and the mutate, this is what we get. So we get the yield, the predicted yield, and the rep, but we do not get a column here for seeding rates. And that's because this model did not include seeding rates. So for me to recover that seeding rate information, I'm just doing a left join to recover that in this model. So if we run that and you print it, you're gonna see that seeding rate comes at the end. And that's because of this left join here. All right, so now we can make some plots. The first one here would be the within group errors are IIDN with a mean 0 and a variance 2. I left you all the code there, so you already have it. You can just run it. We've done this plot many times. So that is just the fitted on the x-axis by the standardized residual on the y-axis. Even though the error bar is comprising 0 on the y-axis throughout, we see there is this increasing residual, right? We have not made a plot yet to see this regression on a plot, but when we get to that, I think you're going to be able to understand why this is happening with the residuals. So just keep in mind that residuals are increasing here, even though they're not different from 0, because the error band is comprising 0 here. All right, so the next plot, I left you the code already, is the QQ plot or quantile plot. There's some deviation on the tails, but really, if I were looking just at this plot, I would not worry much. And then because this is a mixed effect models where we have two variance components, one for the random effect, one for the residuals, we have to check both of those. So next year, we're going to check the random component, the random effects, in this case for block, are IIDN with mean 0 and variance 1. So we've done this already before, so I'm just giving you the code already, not asking you to do much here. but this is how that looks like. We have 4 points because we only have 4 blocks. Again, with 4 points, we're kind of limited to really estimate what the theoretical distribution should be, but here it doesn't look too bad. Finally, I just want to ask for that summary again, just so we take another look at it. And we confirm that our intercept is highly significant. Right, so we see that on the p-value. And then let's do a final plot. I think here I may be asking for your help. Let me see. Yeah, so if we just run what you have right there, this is basically what we had before. Now I do want to run, or I do want to include in this plot the regression line of this model. There are 2 different ways of doing this. I will show you one of them, or that, but maybe there's more than 2 ways of doing this. One of the ways that we have done in the past is perhaps to use geom smooth. However, as you have more complex models, even though you can specify them in geom smooth, it starts to become more difficult to code. So instead of using geom smooth, so that was option 1. Instead of using geom smooth to plot this, we can use our augmented data frame, which has the predictions, and use that here instead. So for us to do that, let's come here, add a plus. I want to use a geom line. So let's call geom line here. Really, the augmented data frame is the one that we already set up at the top level of this ggplot. So this is the one coming through to all of the geoms. We would just have to change what goes on our y-axis. So if we look here on mod1 int augment, which is the data frame we're using, it has the fit.fitted and also has the .fixed column. In this case here, there is a difference between them because this is a mixed effect model. So let's say, well, first let's try to add our .fitted on the y-axis. So because again, this is the data frame coming in already on the top level, I don't have to specify that again. I can just call a yes. And I want for this geom, the y-axis to be my .fitted, which is a column in that data frame. If I run that, I see this line, which is a little bit squiggly. So what's happening here is the fitted is taking into account the random effects and trying to fit different blocks. So that's why we get this like jigsaw type of line. However, the dot fixed, which is also a column here in this data frame, does not try to do that. So if we instead plot the dot fixed column, that is our straight line. So this is the regression line coming from this intercept only model, right? Intercept only models do not allow for different relationships. It's basically just showing you the overall mean on the y-axis, right? That's what we're doing here. Now, one thing that is problematic with this plot, I want to tell you again and bring up a concept we've been talking about in the case of ANOVA. Whenever we create publication-ready plots in ANOVA, I recommend that you do this, that you show, in some way, you show your raw data. This could be with a box plot. We use that a lot already. This could be maybe with a density plot. It could be different ways. But I think it's nice to show your raw data with your statistical summary. On your statistical summary, up until now, what we've been showing for the ANOVA is the letter, right? So the letter separation is something we've been showing here. For the regression case, there's really no letter separation. It's more a matter of, I guess there are 2 ways we could show that for regression. One would be to show the significance of the terms of the model. In this case, there's only one term, if that's the overall mean, or to show error bars around this regression line, which I think for regression makes more sense, is more informative. Our augmented data set does not have any columns here for nothing here is related to, like, if you imagine if we wanted to show like an arrow bar around this line, that is not anywhere in that table. So we have to create that. One way to create error bars around any regression line is to use Bootstrap. Has anyone heard about this term? Is anyone familiar with what Bootstrap is? Okay, so maybe I should share with you some readings so we can read on that, because I really don't have much of a visual explanation here, just in words. But really what Bootstrap is doing is taking your data, taking a sample of your data, and running the model. Then it goes back to it, takes another random sample, runs a model. Does that any number of times you ask it to do, and then for each time that it took a sample of your data, ran the model, estimated the coefficients, now you have a distribution of this coefficient. So let's say I come here and I ask to do a bootstrap of this model 100 times. So it's going to take 100 individual samples of your data, train the model, the same model we're running here, extract the coefficients, and it's going to save that in a cell. And then it's going to save each one of those coefficients for each random draw from this data. And now instead of just having data, you also have a distribution of that coefficient. And because now we have a distribution of this coefficient, which in this case is just the overall mean, we can estimate upper and lower confidence limits on that. That's what we're going to be doing next to create a error bar around this regression line here. And we're going to be doing that for all models in this exercise. So just want to give a heads up. Okay, so that's what we're going to do here in the next step is creating that error band around our regression line. To do Bootstrap, we have to create the levels that we want the models to be trained. I know this sounds a little bit complex for now, but let's go ahead and do this first, and then I'll tell you more in a second. So I want to create a sequence from the lowest hidden rate that we have in this data set, which is 40, to the highest hidden rate in this data set, which is 120, in increments of 1. So let's go ahead and do that. We're going to use the data.frame function, which is what we use to create a new data set. I want to call the first column of this data frame being SR underscore KSHA. Just a heads up is this name here has to be exactly the same as the column that was in your data frame that you ran this model. If this is different, then Bootstrap is not going to work because it has to find the relationship between the actual data and model and the variables in it with what is doing the Bootstrap on. So I want to have a sequence. So for that, we use the SEQ function. Here I say where I start. I want to start at 40. Next thing is where I end. I want to end at 120. And next argument is the increment, the step size. So I want this to be in increments of 1. So if I run this and I just print this ND, and ND is for new data. That's what I'm doing here. If you print ND, you see that we have starting at 40 and going through 120. We have all the observations at increments of 1. One thing to notice here is that these are not the levels. I mean, we don't have all these levels in our study, right? We have 5 levels, 40, 60, 80, 100, 120, but I am creating these fake potential levels all across because I want to have predictions of what would be, in this case, the yield, what is what we're going to predict, what would be the yield predicted at each one of these levels. Another difference between regression and ANOVA. With ANOVA, we do not predict, right? I have my levels and that's it. If I want to know what was the yield, let's say at 45 and I'm doing ANOVA, I cannot do that because I do not have the level. I have a 40, I have a 60, not a 45. Regression allows you to do this, to estimate what would have been the response in between levels of your study, right? So another difference here to keep in mind. All right, so we created our data frame that is basically just our sitting rate. Now let's create some predictions here. really for this model that we're gonna use, it doesn't even have sitting rate in the model. So for this first model, I guess we didn't even need that sitting rate column. I left it here because we're gonna be using this same ND object for all different models, and all the future ones are gonna have sitting rate in them. All right, so thinking about this one here, the intercept only, let's create some predictions here. So I want to overwrite, I guess, on this ND data frame that we created on the next chunk. So we just use the assignment symbol. I start off with ND as well. Let's use a pipe. And so my goal now is to create a column right next to it where we're going to make the predictions of what would have been the yield for each one of these sitting rate levels using the model that we trained above. So we're going to use the function mutate. I want to call this column mod1 underscore yield underscore MGHA. So yield in megagrams per hectare coming from model 1. We give it an equal sign. We're going to use a function called predict. So the way that this function here works, first we have to give it the model. So the model is called mod1 underscore mod. The second thing we give it is the new data frame, which is called ND. And because this is a random effect model where block is treated as random, I really don't want it to give me a prediction for a given model. That's not my goal, right? I don't want it to say, well, level 45 for block 1. If this is a prediction, I don't care about what model, or I'm sorry, I don't care about what block it would need to be. So a way that we can say, give me an overall prediction rather than a prediction for a level of your random effects is just say re.form equals to NA. So this is what tells the predict function, did not give me a block specific prediction, give me an overall prediction at the level of the study. All right, if we run this, oh, I got an error. Let's see what's going on. Oh, mod1 int. Sorry, I had. Yeah, so I had a typo here on my model name is I had mod1 mod and it was mod1 int. So make sure you change that. I just want to print out what ND looks like. So we just overwritten ND. So I just printed that and coming lower here. So notice what happened. It took each one of the sitting rate levels and it made a prediction for them, a yield prediction based on the model that we trained. If we look at this number here, the yield that's being predicted is the same, regardless of the sitting rates. And that is expected, right? Because this model is an overall mean model. So regardless of the sitting rates, it's predicting the yield to be equal to the mean yield, which is this number here, 12.17. All right, so right now ND has the yield estimate, which is already what we have here. So this line is the yield estimate. So up until this point, we have not done anything extra. Now is what is going to come next is I want to ask it to give me the bootstrapped version of this model. So I want to come down to this chunk again, and I just want to show here. To do bootstrap, we're going to be using this boot MER function that it requires our model. It requires a bootstrapping function, and nsim is the number of simulations. I'm setting to 200. I would say that if this is your research, you want to have at least 1,000 simulations on the bootstrap. I'm keeping it to 200 for that to be time efficient on your side. Maybe there are some models here that are going to take more time, even with 200. But again, you want to have this at least 1,000 if you're doing for your own research. Now, because the bootmer function that's going to do the bootstrap requires a predicting function here, I am creating that function right above. We have not covered yet in this class the creation of functions. We'll get to that in a different class. So don't want to spend a lot on this. But really, what I want you to understand is when we give this predict fun right here, this is referring back to this function I'm giving it, which is basically taking the model and plugging that into the predict function we used before. So plugging that model coming through the function here, giving the new data as ND. It's basically doing this. But we have to have this in a function form for it to work in bootmare. When we have that here, it is assuming that whatever model I give in the first argument is going to be the model that it feeds into this function. So in this case, mod1 int is what is going to be coming as mod and be used in the predict function. Make sure you run this chunk. So not the whole chunk yet. Make sure you run this part of the code so you have this function available in your environment. And I left you the code here already for the bootstrap. So what's going on here is we're bootstrapping this model. So the model 1 with the intercept only, using this predict function, which is really just predicting this model on the ND. So ND is what we create above here. And then it is ignoring the random effect part of the model and just getting an overall model prediction here. I just want to run this part only so you see what happens, because I already left you the whole pipe there. So this is the original value. So remember that for each bootstrap run that we're doing 200, it is taking a subsample of our data, running the same intercept model, extracting the intercept value for that one model, and plugging that into this data set. And it's doing that multiple times here for each one of these runs, and is giving us the bootstrap statistics here. So really, this is not something, because it is a intercept only model, things are not changing a lot. But it should have here, so each one of these rows is for one of the seeding rate levels. So for each, let me make sure I explain this a little bit slowly. For each one of those seeding rate levels that we made up, so going from 40 to 120 at every one step, it's running 200 times this model and giving us the statistics of each one of those levels. So each line here is a statistic of 200 models, right? So we basically ran 200 times 81. That's how many models it just ran for us on a different draw from this data set. Now, what I want to do next is, let me come back to my code, is create a confidence interval for those. So if I just run until conf int, let me show you what happens. It's going to give me a confidence interval. So the lower 2.5% and the upper 97.5%. So this would be a two-sided 5% confidence interval around for each one of those 200 models that it ran for each of the 81 levels of seeding rates. So now that I have this confidence interval, I'm transforming this to a data frame. I run until here so you see what's going on. So this just transforms that to a data frame. Now we can plot this because it is a data frame. But before we do that, I just want to rename these two columns here, because these are very difficult column names to call into ggplot or really in any function in R. So I'm just renaming those 2.5% and 97.5% to mod1 intercept low confidence level, mod1 intercept upper. Oh, I have a UPL, but it should be upper confidence level. I'm not going to change that because that's going to impact the code downwards, but it is lower and upper confidence levels here. So make sure you run that mod1 int boots. So if you print mod1 boots, let's see, I think. gonna run that again. Looks like my. All right, so this is what we have now. So we have the lower confidence level and the upper confidence level for where each row here, again, is a seeding rate level that we simulated from 40 to 120. So these are the bands now that I can put around each one of those, of that solid line that was the estimate. Before I do that, I want to bring these results of what mod 1 int boots, which are just the confidence levels. I want to merge that with my ND. So I have the lower confidence level, the estimate, which we have already predicted previously, and the upper. So lower, average, upper. If you just do a bind calls and you print ND, you should see this. Now we have seeding rate, we have mod 1 yield, mod 1 lower confidence level, mod 1 upper confidence level. So now I can use all these three columns to create the regression line and the bands, the error bands around them, which we're going to do here next on this final plot. So if you just run what I left you, this is what we get. This is basically what we already had on the previous plot. I did not change anything yet. The next thing I want to add here is the error bars to this plot so we can look at them. I think I'm going to decrease my font size just so we can see more of my code. To do that, we're going to use a geom that I don't think we have used in this class yet, which is called geom ribbon. So with geom ribbon, we need to tell it what is the, so a ribbon, imagine like a, I don't know if you all know what a ribbon is, but it's basically like a tape, sort of like a shape of a tape, right? So imagine a tape where you have like upper and lower limit of that tape. We need to say on geom ribbon, what column has our upper limit of the tape or the ribbon, what has the lower limit of that. So let's add a plus. Let's call geom ribbon here. The data is going to be equals to ND. Remember, ND is where we binded the columns of the intervals coming from boots with the estimate that was already in ND as we predicted that above here. So this is getting our estimate, predicted estimate of the model. So the model line, and the boots is giving us the confidence interval around that estimate. So geom ribbon data equals ND. Let's call our AES function here. So really the only thing that is changing here is we need to give our Y min. So Y min argument would be the lower boundary of the ribbon. If I print ND below here, so we look at it again, Y min should be our mod 1 int LCL. LCL is lower confidence level. So that's what our Y min should be. We also need to tell it what is our Y max. So Y max would be on the Y axis. What is our upper limit of the ribbon? In this case here, that column is called mod 1 int UPL. I want to get outside of the AES, so make sure that you are after the parentheses that closest AES. You can check that by the blinking parentheses if you toggle or move around it. I want to have the fill to be equals to gray. So just doing some small changes here. I want to have the alpha, so the transparency to be equals to 0.5 so I can see through it. And let's see if that works. Okay, so we're saying that, let's see, what do I have here?
Your ggplot has one that is not in the other.
Yeah, so here we probably have to change our Y. So in this ND, so on ggplot, our Y is the yield milligrams per hectare. On ND, our Y should actually be this column here. So the mod 1 yield milligrams per hectare. So if you come back on AES, we would say y equals mod 1 yield milligrams per hectare. And that should work. Yeah. And this is, I guess, a good example. So because we have defined our X and Y variables on the ggplot level, oops. Sorry, come back. So because we have defined X and Y ggplot level, those carry through downwards, right? So in this case here on the ND, I did not have a column yield milligrams per hectare, but I do want the mod 1 yield milligrams per hectare. So that's why you just have to change that and let it come through. All right, so if you run it, these are the error bands around this regression line. So now we at least are showing a metric here of certainty or uncertainty around this. Just want to leave the code for you a little bit there so you can take a look if you're still catching up. All right, so one thing, well, if anyone needs more time, let me know. I can wait here for a second. Anyone has any questions? So I guess just, if we just talk about Bootstrap again, I will send you some reading materials so you can understand better. But what we're doing here is just going through again this chunk again. We're going to be doing the same step for all the different models. And I think this perhaps is the best time for us to talk about it in more depth and so you understand what's going on. So we created this empty data set with different levels of seeding rates that we want to make a prediction for. And I'm just have this in a more finer scale than our actual treatment levels were, because this is a regression exercise. I want to know that continuous behavior of seeding rate and impact on yield. So that's why I'm asking from the lowest seeding rate level to the highest in increments of 1. This could be increments of 0.5 or 0.1 or whatever you wish, right? The smaller is the increments, the more detailed regression line you're going to be able to predict. I think 1 for this case works well. So that gives us 81 rows that we're making predictions for. The first thing that we predict for is the estimate, the mean of that prediction, right? So we are making a prediction here of that mean, which is basically just that black line. That is the mean prediction. But then I also want to have the error bars around this line. So for that, we need Bootstrap. What Bootstrap does is, in this case here, we're asking it to, for each one of those seeding rate levels that we created above, I wanted to run 200 models where for each time it takes a sample of your data with replacements, meaning that it's taking a sample of points that could repeat themselves. This is going to be a little bit difficult, I guess, to show in words. So maybe the reading material is going to help with this. But it's taking, let's just think it's taking a sample of your data, fitting that model, extracting that estimate of the intercept, taking another subsample, fitting another model, taking that other estimate of intercept again, and doing that 200 times for each one of our seeding rates. In the end, we have a distribution of your intercepts for this model coming from this random sample and this training of multiple models over those samples. Because we do have a distribution of that, now we can ask for confidence intervals around it. So it gives us for each one of our seeding rates, which the Bootstrap ran 200 models for each one of them. Now we ask for the lower and upper confidence level for each confidence, I'm sorry, for each seeding rate. So it's doing that over all the 200 models that were ran for that seeding rate and giving you this lower and upper limits here. Now these become the extremes of the ribbon, which represents our error bars. So this is the upper, this is the lower, and this was estimated for the different. You know what, maybe let me show you something different here. Let me see. Let me do something slightly different here. So if I do a geom point, you don't have to do this. I'm just doing to try to show you what I mean by some things. So if I, nope, don't need a filter. So my Y is going to be yield. My X, I want it to be one of these. And I just want to color that red. Wow, that did not do what I thought it would do. Maybe I'm doing the wrong thing. No, yeah, this is not my X. This is what I need. Okay, so just to maybe create a little bit more of the understanding here. Even though we're asking for it to show us a ribbon, which does a line across, but really all the lower and the upper that I'm not showing here are just points, right? It's because these points are the predicted lower confidence level for each one of the 81 seeding rates that we gave on the ND. So when I ask for a ribbon, it really just makes a line across them, does not show us the points, but these points are what are coming from the ND, right? So ND here, for each seeding rate, I had a point that represents the lower confidence level and a point that represents the upper level. But when we use that in the ribbon, it's just connecting those points and showing us. So there are points, and I just did this extra here just to perhaps help you understanding, but the ribbon is just showing us those points connected, both for the lower and the upper. All right, any questions about this? Yes, Niva. You're saying it looks like random forest? So random forest mechanism, we're gonna get to that when we start talking about it. It actually, it does a random sample of both your columns and your rows. And so it is similar in the sense that it's taking a random sample. But random forest does this differently because so it does that sample. So here we're just sampling rows. Random forest would be more on the multivariate aspect where we have multiple columns as well. So random forest would be sampling rows and columns and using that to train each tree. And it does that to train multiple trees, which could be, so in this case here, you know, we can kind of think that if this was a random forest model, we would only be predicting the intercept only. So it is similar to some extent. Perhaps the main difference is that random forest also samples the columns, and here's just the rows. And also because random forest in the end is going to give you a prediction that is the vote across all trees. And here, I guess we can kind of think of this as vote as well, because it's just being the average. Yeah, so they're actually, they have some similarities there. I never really thought about it, but that's a good point. So they do have those similarities, and the more I'm talking, the more I'm thinking, maybe one of the main differences would be random forest also samples the columns rather than just the rows. Yeah. All right, so before we move on, I just want to make a point here that, so what you saw if we go back to the beginning here, when we start running this model. So I just came out on the intercept only. We ran this model. The intercept was highly significant, right? So I guess keep this in mind. The intercept was highly significant. We checked the assumptions. Here, even though it seems like there is something going on, but you know, it's not different from zero, the band. There's really nothing looking too terrible in these residuals or these. So really, residuals look okay. The model was highly significant. So if we were to run just this model, perhaps we would say this is a good model, right, for this. However, when we look visually and we assess visually, we can definitely tell that this may not be the best model, right? And this is what I urge you to always look at your data, always plot your data, so you have understanding of what's behind it. Because just looking at p-values, just looking at residual plots may not give you the full picture. So even though this model was significant and there was really nothing terribly wrong with it on the residuals, it's probably not the best model. Okay, so I think we can get started with the linear model here. There's a lot of the same things I left you in the code, so I just removed things that will require us to change to implement a different model. So if you come here on the next chunk, we're gonna run this model and save that in this object called mod2lin. So it's our second model and it's the linear model. And again, when I say linear in this case, I'm really referring to the fact that it is a intercept plus slope model. Because really the previous model, if you consider in relation to the parameters of the model, both of them are actually linear. All right, so if we come here, let's continue using LMER. I want to again just come here and print our data set, which is the reg underscore DFW. So we look at that. We're going to have our yield being explained. Again, we want to have the random effect of rep. So you can go ahead and do that using the correct notation. And now the difference between the intercept only and the intercept plus slope is that we're going to give the seeding rates in KSHA as our fixed effect part of the model. Right, so this is what determines that now we have an intercept plus slope model, is that we have another variable in this model, and this variable is numerical. This is what's going to give us a slope. If seeding rate was categorical, it would not give us a slope, it would give us the mean of each level of seeding rate. Because seeding rate is numerical, it's going to give us a slope. So make sure we also save the data. So data equals reg DFW. All right. So if we run this model now, we check the summary quickly here. It's going to have here on the random effects the same thing as before, the wrap and residual. On the fixed effects, now there is a difference. It still has the intercept, but now it has this line here for seeding rate. It has an estimate of 0.05. This estimate is the slope. So the slope of this relationship is 0.05. And both of them are highly significant as well, as we see on the p-value. All right, I left you the code for extracting the residuals, calculating the standardized residual, so we can go ahead and run it.
Dr. Bastos,
Yes,
could you just go back up that previous chunk? I think I missed something there. I'm sorry.
this one here. All right. So extract the residuals. Looking at the error residual assumptions, if you run that, this is what we see now. So remember, these are the residuals. So we're doing fitted by standardized residual. We see this clear pattern here that is quadratic. I want to take a moment here to talk about this. what are the two main cases where we may see patterns in residuals? One of them is you have dependence on your observations and therefore on your residuals that you're not modeling. Like, for example, repeated measures, right? We covered that previously already, how we would take care of that. In this case, this is not a repeated measure exercise. We only measure one time, and there's no time variable in the model. What is happening here is we are missing a model parameter in this model to best describe this data. Normally, when you see a pattern like this, it means that you're missing, when you see a pattern like this in your residuals, it's telling you that you're missing a quadratic term in your model, which again, we do not have that yet. Right now, we just have an intercept and a slope. And the residual is a difference again from the points and the line. So if your residuals are showing a quadratic pattern and you don't have repeated measure because you know it based on the model, then it's most likely an issue that you're missing a parameter of your model to describe this relationship. So you're not accounting for that in the model, which means it's transferring into the residuals. That's what we're seeing here. Something that also I want you to notice is, and I know I've told you this many times already, so I hope you already are thinking about this. Residuals change if you either change your data and or your model. We're not changing the data, we're only changing the model. So if you look at this same plot for the first exercise, for the first model that we had, it's not gonna have this shape, right? So it's gonna have this shape here. So residuals change every time we change the model, and that's why we should check the residual assumptions and not the raw data assumptions. Okay, I just want to go back to where I was, which was right here. So we see a clear pattern here. There is a little bit of non-overlap with zero. Perhaps, it's not like a very, very strong pattern, but we do see there is a pattern, and we know why. Because we already looked at the data on the EDA. We know that probably a quadratic model fits best because this model is not quadratic yet. This model is just intercept and slope. We know we're missing that quadratic term in our model, and therefore that's probably the solution in this case. All right, let's look at the QQ plots. So I left you the code there. Now we can see that we have perhaps a stronger deviation of the normality assumption on this QQ plot. We have a lot of points on the lower and upper tail deviating from the line, which is starting to get a little bit more problematic. Before, if it was just a few ones and they were like, not too far, not too strong of a pattern, it was okay. In this case here is a little bit uglier, I guess, compared to what we've seen before. And then looking at the random effect, again, it's hard to really tell much about here because we only have 4 points, but at the same time, nothing here is looking too terrible. So really on this plot, on this model, the fact that our QQ plot of the residuals are looking off on the tails, and also because I see this clear pattern on our fitted by standardized residual, this is telling me this model is not the best for this data. So again, if we just look at the summary here, just to remind you that now we have an intercept and a slope. And again, because seeding rate was numerical, this estimate is a slope estimate. If seeding rate would have been factor or categorical, we would have 4 entries here for seeding rate associated with the mean at those levels, which is what we were doing before when we're talking about ANOVA. And also the fact that they're both highly significant, right? So again, we have another model where both terms are highly significant, yet may not be the best for this data. So the final plot, I think let's see, I think I may have removed something from this code. Let me just look at on my side. Yeah, okay, so the only thing that so we have here the points. I want to add just the estimate here. So if you remember the estimate only, so without caring for the error bars, the estimate is something that we can get from the augmented data set, which is what is coming already through this ggplot. So let's just add plus. I want to do a geom underscore line. I call AES. I want to have my Y to be equal to, in this case here, so we tried the fitted before. If you remember, that kind of touches all of the estimates of your blocks. So to avoid that, I want Y to be equals to dot fixed. And then I come outside of AES, I just want to say color equals to blue. So this is how our plot looks like. And imagine now if you are calculating the distance between each one of the points to this line, that is your residual. If you were to calculate that distance and plot them as we did, you would see that quadratic pattern in your residuals. Again, that's because our model is not properly parameterized. It is missing a quadratic term that, because the model lacks it, it is showing on the residual pattern. All right, so I also want to come here and calculate the error bands around this. I think we can probably finish here. And I think I left you most of the code already because this is the same thing. The only thing, so now we're taking ND, which is our data set that now has hitting rate, but also has the estimate yield of mod 1, the lower and upper limits of mod 1. Now we want to do the same thing. So we're going to have 3 more columns where we're going to have the estimate of model 2, upper and lower limits of model 2 as well. To do the estimate, we're just using that first part where I'm predicting. I'm calling this column here mod 2 yield megagrams per hectare, predicting model 2 just like we did before. So if you just run this first part of the code and you print ND, now in the end, you're going to have your model 2 prediction of yield. Something to notice as well is for model 1, so mod 2 yield and mod 1 yield had the same number for all the yield levels here because it was an intercept only. So it is assuming that the prediction of yield is equal to the mean yield for that model. Model 2 now is an intercept plus slope model. So this number is the estimate of that model is changing as you change hitting rate, as you would expect, because the model has that slope term. So that's what we did right there. And then this next function here is just to get the upper and lower confidence limits doing bootstrap. So it's doing the same thing as before, but now it's using model 2 to make those predictions instead of model 1. So if you run that, it may take just a moment to go through, but then it goes through. And so we assign all the bootstrapped confidence limits to this object called mod2 lin boots. Now I just want to bind the columns of that with our ND. So now if I print ND, it has the estimate, lower and upper confidence levels of mod 1, the estimate, lower and upper confidence levels of model 2 as well. And then I left you the code here for us to plot that, as we have already done this, with the difference being that now my Ymin and Ymax of ribbon are the mod 2 lower and upper confidence levels. So if you plot that, this is what we see. So this would be what I would show in a paper. I do think it's important to show error bars, so we would show them this way, doing bootstrap, calculating the confidence levels on it, and showing that as well. All right, I think this is a good stopping point. We go to 11:10 today. So next class, we'll finish running the quadratic regression model and also the linear plateau model. I'll be right there with you. And then we're going to select what's the best model for this data set and use that to estimate the optimum yield level in this case. And that's going to wrap this exercise up. Yes.
If we try to force the geom smooth to fit a linear model, would the confidence intervals be the same as the ones we calculated with construct?
That's a good question. So Jonathan is asking if we can force geom smooth to fit the same model that we're training, would the confidence levels be the same? I don't think they would be necessarily the same. I believe geom smooth is using some type of bootstrap as well, but because bootstrap involves resampling, and that has like a random component to it, like a random sampling component to it, I don't think they would necessarily match, but I think they would be similar. So if we, if we come here and we just do a geom smooth with the method equals ln. Yeah, so it's not the same. The estimate is the same, but the errors around it are not the same. This could be related to the fact that I ran 200 simulations only. Maybe if we run 600, that may be different. Let's see what happened here. CL 1, 2. Oh. Did I? Yeah, I probably just overriding objects. Yeah. Yeah. So maybe we can check that another time. But yeah, maybe if you increase here the number of simulations, it will get closer to it, but perhaps not match exactly. All right, let me just remove this so I don't confuse anyone. Any other questions? All right, I don't hear anything. So I'm gonna open up for attendance. Attendance, March 12th. All right, just submitted that. And so claim your attendance before you leave. And I just want to tell you again, I'll share with you the assignments either today or tomorrow for the project, so you can start working on it. And just as far as the class goes, so we are right now talking about linear and nonlinear regression and those response optimum finding. So I think we're going to finish this by Thursday, and then we're going to get into iteration. So there are different ways to do iteration. If you've been working other languages, you may be familiar with loops. So there are for loops, while loops, other types of loops. That's one way of doing that. We're going to see a little bit of that, but then I will expose you to a different way of doing iteration in R, which is using a tidyverse style of iteration. After that, we're going to start getting more into machine learning. So we're going to start, we're going to get exposed to a data set that is geospatial in nature, and we're going to use the coordinates of the data set to pull from open source data sources for weather and soils data. So then we're going to be exploring APIs for different open source data, creating new variables out of those, which is feature engineering, and then start getting more into the machine learning side of things. So right now we're in this transition between experimental data, regression, and then really getting into machine learning. All right, if you have already claimed your attendance, you're good to go. Let me know if you have any questions, and I'll see you on Thursday.